Hello! I want to take a few minutes of your time to talk about quantum statistics and also some cool quantum phenomena. Without further ado, let's get right into it. Let's start off with quantum statistics and how we can use it to examine why carbon monoxide poisoning happens. Carbon monoxide is incredibly dangerous since it's colorless, odorless, and tasteless. Ultimately, carbon monoxide poisoning is a result of deficient oxygen transport and poor tissue uptake. But why? Well, I'm glad you asked. I'll tell you why. Inside of the body, hemoglobin sites are responsible for carrying oxygen in the blood. Each of the 4 adsorption sites can accept 1 molecule of oxygen. If just oxygen is present, then there are only 2 possible states, occupied and unoccupied. You can then use quantum statistics in the form of the Gram partition function and the Gibbs factor to calculate the probability of oxygen binding to a heme site. The probability of oxygen binding when no other possible molecules are around is about 98%, which is really good. But what if a small amount of carbon monoxide was present? You might actually be surprised to find out that simply having carbon monoxide in your blood lowers the probability of oxygen binding to only 25%. And that's due to the fact that carbon monoxide has a higher binding energy with the hemoglobin sites, and so it makes it really near impossible for oxygen to bind to the blood cells. So carbon monoxide is literally suffocating your body and preventing oxygen from binding to your red blood cells. I want to take a moment to go back in time to talk about the Pauli exclusion principle and the symmetrization postulate. Wolfgang Pauli came up with the Pauli exclusion principle in 1925, and it states that electrons must have opposite half-integer spins of 1/2 and -1/2. You can see from this example of an orbital diagram for phosphorus how this works out. So in each orbital you can see 2 electrons, and one is spin up and one is spin down. Those correspond to 1/2 and -1/2 spins respectively. Notice in the last 3 orbitals how all of them are spin up and none of them are in the same box as each other. You might be asking yourself why that is, and I'm here to tell you why. This is a result of Pauli's updated principle, really, to include all fermions. So his postulate then became that 2 or more identical fermions cannot occupy the same quantum state. And so we see that in the 3p orbitals, that none of the fermions want to be around each other if they can help it. So they all go to their own respective boxes before they end up flipping spins and going in the same box as another electron. You might have heard me mention fermions in the previous slide, but really, what are fermions, and what are bosons also? Well, fermions, like I had mentioned, fermions have half-integer spins, and they have antisymmetric spin states. Bosons, on the other hand, have integer spins and have symmetric spin states. And you can see from this picture how fermions and bosons like to behave. So fermions don't really like to be around each other if they can help it. So you can see in this graph there's particles and they're all filling different energy levels, and that's because they really don't want to be around each other, and they'll just keep filling up energy levels up and up and up. However, with bosons on the left, bosons really like to be around each other, and it actually is way more beneficial for them to be together, as we'll talk about next. Helium-4 is an isotope of helium that has 2 protons and 2 neutrons. Because of the integer spin, helium-4 is a boson. When helium is at room temperature at about 300 Kelvin, there's a relatively small fraction of molecules in the ground state. However, at the very special temperature of 2.17 Kelvin, helium-4 becomes a superfluid. A superfluid has 0 viscosity, which means that it has no friction. Superfluids are also capable of escaping out of the smallest holes even in a completely sealed container. Superfluid helium-4 is an excellent thermal conductor as well, and it's actually better than most metals. Helium-3 is another isotope of helium, but in this case it only has 1 neutron. This makes helium-3 a fermion. Helium-3 is showing promise as an alternative fuel for fusion reactors. In current prototypes, tritium and deuterium are used. However, there's a lot of energy lost through this fusion process. Helium-3 has the benefit of keeping more of the energy in the reactor, and the products are only helium and protons, same as the deuterium-tritium reaction. And that brings me to the end of my presentation. I hope you learned something new, and thank you for watching.